There we go.
Can you hear me?
Yeah.
Okay, gotcha. So these biophysical representations are very important for us to understand how the forests are responding to climate change by looking into these specific parameters. So in the last few decades, the Earth observation has made huge progress and allow us to have vast amount of data in combination with machine learning to apply that for forest monitoring. However, the traditional statistical learning approach often is not able to yield the interpretable biophysical representations, as I mentioned before. So this has restricted its applications to start to monitor the forests in order to get these biophysical variables. So if the traditional statistical learning is not able to do the job, so how can we obtain these biophysical variables? So of course, the first idea to mind maybe to do the field work. So you can bring your measurement instruments, go to the field to do the measurement. But it also has some downsides, like first it's slow. Also, I mean, the human resources nowadays is quite expensive. So it can be very costly. And so the approach is not very scalable. Alternatively, in the domain of remote sensing, scientists have developed some physical model in order to get these biophysical variables. So the model specifically that they use is called radiative transfer models, which essentially models the canopy and radiation interactions. So as you can see from this slide, let's say the model, we call it F. So given the input, which are all these biophysical parameters, it will simulate you, give you the output, like what the satellite spectra will look like. So given this model, by inverting this model, people hope to retrieve the biophysical variables. But actually inverting the RTM is actually a not easy question because it's not uniquely invertible. Like what I've showed you in the previous slide, for the say kind of like the same shape of the satellite spectra, you can have different combinations of the biophysical variables. So given the same input of the satellite spectra, there could be different groups of biophysical variables that will result in the same output. So inverting it is a bit hard. So there are several approaches people have developed over the past few decades, including like numerical optimization, a lookup table, and neural network regression. So the neural network regression is regarded as the state-of-the-art approach. What this work does is that first it do the data sampling. So using this RTM, so they sample a set of biophysical variables, and then they simulate the satellite spectra. So they have a synthetic data set. And then they use the simulated spectra as input to train a regression model to predict the biophysical variables. But this approach has a very significant drawback, especially in the forest scenarios, due to the systematic biases of the RTM. So what is systematic biases? It's actually the discrepancies between the simulated and the measured spectrum. So if you have a real-world biophysical variables and the real spectra, you get input, you use this variable as input to the physical model, but the simulated spectra has discrepancies between the simulated and the measured one. This is because any physical model, including the RTM, is built upon simplified assumptions because it's impossible to model every aspect of the canopy radiation interactions. So in order to have a physical model, we have to simplify our assumptions to only model certain aspects of these interaction relationships. But this systematic bias is especially significant in the forest domain because in the cropland it's not very significant because the structure of the cropland is more uniform than forest. But the forest structures has more complexities, which makes this systematic bias more significant. What it means is that if you use a simulated spectra as input to this neural network regression model, the variables you get is not accurate because the input has biased compared to the real spectrum. In response to the challenges I mentioned above, different from the traditional approach. We draw inspiration from the physics-informed machine learning and disentangled representations by integrating the RTM into an auto-encoder structure. By doing so, we hope to have an end-to-end learning, and also we have two important objectives. One, we hope to correct the bias I mentioned above. Two, by correcting the bias, we hope that it will allow the model to learn more accurate retrieval of the biophysical variables. So how we are going to do that? The specific model we are going to use is called Inform, which was developed by Clement before. Inform, this RTM, this radiative transfer model, it has a group of sub-models, including like leaf model, canopy model, forest model, to describe the biophysical and geometric features at different levels. So using these things as input, it's able to simulate the satellite spectra. But due to the ill-posed nature I mentioned before, and also the correlations of the variables, so we decided to learn only a subset of the variables. There are 7 variables in total we decided to learn, but directly within the known ranges. For the rest of the variables, we decided to fix them as the typical values for the study area. So this table shows you the variable we are going to learn and variables we fix to constant. So taking these variables as input, we use the Inform to simulate 11 spectral bands of Sentinel-2, which we will use in our study. So Sentinel-2 has a spectral band that cover from the RGB range, near-infrared range, and shortwave range. The data set we are going to use come from Austria. So it contains the individual spectra that are extracted from different individual sites. And it covers, for each individual site, it covers 14 temporal steps. And also every spectra can be like the trees from which the spectra get extracted. Those trees can be attributed to 12 species, and which can be further clustered into 2 forest types, including coniferous and deciduous forest. So it's important to mention that it's very challenging to get the direct ground truth of the biophysical variables for validation, which is also why the reason people prefer to use the RTM to invert the RTM to retrieve the variables. But it's still possible to validate how our model performs by using the information I mentioned before. For instance, we have the temporal information. So after retrieving the variables, we can check the consistency of the temporal variations of the variables. We also have the species information and the forest type information. So we can check whether the biophysical patterns contained in the learned variables, whether they are aligned with the prior knowledge of species and forest type. We can further study how disentangled the learned variables are. To learn the inverse, let me first introduce you what the classical autoencoder do. So it essentially contains 2 parts, an encoder part, a decoder part. It takes let's say, the spectra as input and embed into a latent dimension, which is often reduced dimension as a dimensionality reduction. And then it decodes the embedded features into the reconstructed spectra and compare the reconstructed spectra to the input spectra. But in this classical autoencoder approach, it only learns some latent codes as a compressed representation of spectra. It does not carry any biophysical meanings. So we decided to replace the decoder with the radiative transfer model, or the Inform I mentioned before. So in this way, the encoder has to embed the input spectra to the biophysical variables, and then the decoder, which is the Inform, will take these biophysical variables as input and then output the simulated spectra. Then the simulated spectra will be compared with the input spectra to train the model. But as I mentioned before, this RTM has systematic bias. So accordingly, the simulated spectra also has biases. So to correct the bias, we have added some nonlinear layers after the info model. By doing so, we hope to achieve like the objectives. First, we hope to that after the originally simulated spectra being passed to this nonlinear correction layer, the corrected spectra is more accurate compared to the input spectra. Also, by this bias correction, we hope that it can refine the learning in the latent space of the variables. Any questions so far? You have? Okay, so far I have introduced you to the basic idea of our approach. It's not complicated and also represents the RTM as like a kind of like a black box model. But actually, it's a bit challenging in practice to integrate this RTM into our machine learning pipeline because the original inform, which is implemented in NumPy, contains like NumPy arrays and operations, which is totally fine for its original use because it's an integrated module in QGIS. But in order to integrate that to the machine learning training, like the pipeline I mentioned before, to integrate that to the autoencoder, we need to convert the info into modern machine learning pipelines like PyTorch, because PyTorch can track the computational graph layer by layer, and it also has defined how to calculate derivatives for each operation, so it can allow you to do the backpropagation. But manually converting this model is very complicated because it contains let's say the scripts from different submodels. In total, it counts for 1742 lines of code. If I do that manually, I can work it months, and then I can now stand here to present here only how I convert the NumPy implementation to PyTorch. This work was done in May last year when GPT-4 just came out. So we decided to test out the large language model's ability to convert the NumPy version to the PyTorch version. It turns out to be very useful that GPT is able to convert the commonly seen operations of NumPy to PyTorch. But when the conversation gets longer and longer, it can also make some mistakes. But the fortunate thing is that it can allow you to do a kind of like a prompt engineering by doing conversations to say, hey, next time when you do the conversion, if you are not certain about certain parts, could you point out to that specifically so that I can look into that further? So let's say for this one, in the original NumPy version, there is a exponential integral function in NumPy, which is not implemented in PyTorch. But after the conversion, GPT can say that I found this function is not available in PyTorch, so I can further to take a look and manually implement the PyTorch version by myself. So after converting the inform to PyTorch, we can now do the machine learning. So this is a full overview of our model architectures. So it takes an input of the spectrum, passes that to the encoder, which contains, let's say, the linear layers and value. Also, its original output is just a scaling factor from 0 to 1. And then it rescales that using the known ranges of these variables to output the biophysical variables. And then these variables pass to the RTM to have the originally simulated spectrum. And then it's further passed to these nonlinear layers to correct this spectrum. And then this final output spectrum will be compared to the original spectrum to train the model. And so, as I mentioned before, we have converted the info to PyTorch version. So the whole pipeline now is fully differentiable, which will allow us to do an end-to-end learning. Now, of course, it's very important to have some baseline to compare with. So as I mentioned, the neural network regression is the state of the art. So here we replicate the state-of-the-art approach. We first sample the data set to have a synthetic data set using the RTM. And then using the simulated spectra and the sample variables, we train this neural network regression model. Its architecture is essentially the same as the encoder of our model. So this neural network regression, we call it NN regressor. It will be trained on the synthetic data set. But to compare that with this baseline with our model, it will be evaluated on the real data set. So it's not end-to-end, so it contains 2 steps. It will take during the evaluation, it will take the real spectra as input and estimate the variables for that. And those estimated variables will be compared to the variables retrieved by our model. Also, the variables retrieved by the NN regressor can be used as input to the RTM to get the reconstructed spectrum, to compare the reconstruction accuracy. So how the model works? Before diving into that, I want to first show you that our PyTorch version is actually reliable. So we validated the PyTorch implementation of info by simulating 10,000 size of variables and spectral bands and passing through them into the NumPy version and PyTorch version respectively to compare the outputs. And we think that is essentially equivalent to the original NumPy version to be used. So for the bias correction part, we first look into the reconstruction accuracy. So as I mentioned, for the NN regressor, it's trained on the synthetic data set. So but evaluate on the real data set to estimate variables. So we only have the MSE, like the mean squared error of the NN regressor on the real test set. As you can see, the reconstruction error of the NN regressor is more than a magnitude higher than our model ARTM core, but this can also be visually verified. These plots show you the one-on-one plots for all the input and reconstruction bands. On the left side is the plots for the baseline model. The right side is our model. The x-axis is the original input spectra, like the real spectra, and the y-axis is the reconstructed spectra. So as you can see, the reconstruction from NN regressor displays clear bias. For example, in the middle row, in the near-infrared range, it seems that the model tends to underestimate the simulated, the simulation. But with the bias correction layer, our model is able to reconstruct the spectra more accurately. And also we look into how the bias works exactly by comparing the originally simulated spectra with the corrected spectra. So to do so, we use the variables learned by our model and use that as input to the RTM to get the originally simulated spectra. Then we subtract the corrected spectra by the originally simulated spectra to derive the bias. So this plot on the left shows you the distribution of the biases clustered by the forest type. So as you can see, the patterns are also distinct between forest types for most of the bands. And on the right side are plots the spectral signature for different forest types. So as you can see, for the coniferous forest, it seems that the RTM, like the info model, tends to overestimate the spectra because the initial spectra, especially in the near-infrared and some of the shortwave band range, it tends to be higher than the corrected spectra. But for the deciduous forest, it tends to underestimate the spectra. But bias correction is important, but its ultimate purpose is to help to refine the learning of the latent variables. So here we evaluate the impacts of the bias in learning these variables. On the plot shows on the top is retrieved variables from the baseline model NN regressor. As you can see, by applying the NN regressor to the real Sentinel-2 spectrum, many of the values of the learned variables fall into the limits of the known ranges, which is apparently implausible distributions. But with bias correction, our model is able to learn more plausible and more plausible distributions, and is distinguishable between forest types for some of these parameters. For instance, for the structured parameter n, the first subplot, the value of the coniferous forest usually smaller. Its distribution is tend on the left side of the deciduous forest, And for the fractional coverage, the coniferous forest is tend to be higher than the deciduous forest. Is distinct between different forest types. Also, we evaluated the physical patterns of the learned variables. So to do so, we plot the pairwise co-distributions of the learned biophysical variables, because we have 7 variables to learn. So this plot shows you the 7 by 7 pairwise co-distributions. And we cluster that by the forest type. The red color means coniferous forest, blue color means deciduous forest. We found it provides us with some interesting insights about the physical patterns. For instance, the one highlighted by the red box, the LAI has an apparent negative correlation with the LAIU. So LAI is a leaf area index, which quantifies the canopy, which can represent the canopy, the plant growth in the canopy level. And the LAIU can quantify the plant growth in the understory level. So this is interesting because higher LAI, meaning like the higher plant growth in the canopy level, can reduce the light penetration through the canopy. So it will result in the lower plant growth in the understory. Thus, we have the negative correlations. We also further evaluated the temporal variations of the variables learned by our model. And we found that our model is able to learn distinct and temporally smooth variations for different forest types. So again, if we look into LAIU and LAI, we find that from April, the LAI starts to increase. Let's say the canopy growth, the plant growth in the canopy level starts to increase, and correspondingly, the plant growth in the understory level starts to decrease from April. Also, for the coniferous, if we look into the fractional coverage, that's the last subplot, which means that the total area of the tree crowns in the unit hectare, the coniferous forest has higher fractional coverage and less variations over time. We also evaluated the disentanglement of our learned variables. So, because we have learned 7 variables, and these variables can be clustered by the 12 species. So, which means that each species can be represented by a 7-dimension distribution. Each dimension is a single variable, right? So we can calculate the pairwise Jeffreys Matsushita distance between species that are represented by these learned variables. So this GM distance essentially quantifies the separability between 2 probability distributions, and its value ranges from 0 to 2. So the higher the value is, the more separable the 2 distributions is. And so this plots on the left shows the pairwise GM distance of the baseline model. The one on the right shows the one learned by our model. And the red font represents the coniferous species, and the blue font represents the deciduous species. So as you can see, the GM distance learned by our model is usually higher than the baseline model, which means that our model is able to learn more disentangled representations. And even within the forest type, because you can see there are some clustering group patterns for the coniferous forest or the deciduous forest, their GM distance is smaller. But even within the same group, forest type groups, our model tends to learn more disentangled representations. So it seems that our model has effectively corrected the bias and learned variables. But so to further evaluate the different effects of our experimental design, we conducted an ablation study. So in this table, I have evaluated the MSE, like the reconstruction loss of different design steps along our pipeline. So the first row is the classical auto-encoder approach without RTM, without correction, the MSE loss we got on the test dataset. Then we replace the decoder with the RTM, but without the correction. As you can see, the MSE loss, the reconstruction loss is more than a magnitude higher than the original loss. And then with the RTM, but also with the correction, which is our final model, we find that the MSE loss is comparable to the classical auto-encoder approach. But this bias correction also allow us to compare like the variables learned by our model with and without the bias correction. So without the bias correction, it seems that the variables learned by the model have a similar shape as the baseline model and regressive, because it's hence that many values falls to the limits of the range. And it's probably due to that in order to minimize the reconstruction loss, but also despite of the presence of the bias, the model, it has distorted the distribution to extreme values. But with the bias correction, the model is able to learn more possible distributions. So to sum up, we have developed an end-to-end learning approach to learn biophysical variables from satellite spectrum. We achieve this by integrating a complex radiative transfer model into a modern machine learning pipeline. And by the design of the bias correction layer, we have also significantly improved the reconstruction loss, which means effective bias correction, and which also results in more plausible recovery of the biophysical variables. And I think our approach, including the forward pass to learn the variables, as well as the back propagations to calculate the gradients, also has a broader implication for inverting biased physical models. So if you can think of any other biased physical models, you can let me know and we can test our pipeline again. So in the future, I think we can further improve the temporal consistencies of the retrieved variables. Also, currently we only learn 7 variables, but you have seen from the table, there are more than 7 variables to learn, but they have correlations. So we hope that we can address the correlation issues and learn more variables at one time, if possible. Thank you very much.
We have quite a bit of time for questions, so yeah. No. Firstly, very, very impressive. Congratulations. Can you just tell me a bit about the field data so you mentioned Austria. So did Clement go and collect data from a whole lot of sites in Austria, which was used in this modeling? Well, just tell me a little bit about that.
Yeah, so Clement provides data to me. So I have limited information about how he collected data. That data, what I know that they extract the spectra from the single pixels. So they have the spectra, which is not the image, but the single spectra with corresponding
the Sentinel-2 spectra.
Yeah, with corresponding species and timestamp information. Yeah, it's from Austria. So actually, there's some more information to add. So we learned 7 variables, but for the other 2 variables, originally we wanted to learn that, but we found that due to the correlations, difficult to distinguish between them. So we learn 7 variables, then we use a fractional coverage and we fix the stem density, and then we use a fractional coverage to calculate the crown diameter. And then we use the database you collected before, like the allometric database, to derive allometric equation between the crown diameter and the canopy height. Then we decide the canopy height. And for this, we filter the database by using I think the temperate forests, because we think that it's mainly covered in the Austria to do that.
Can you, I'm sure other people have got questions. Can you go back about 6 slides where you compare the distance between PDFs? That one wasn't 6, was it? So Larix decidua, as the name suggests, is actually a deciduous conifer. So it's a conifer, but it's a deciduous one. And so actually, if you move it one across to the right, sitting in next to the deciduous ones, it looks to me like it. I think that's good news. I mean, it looks different in the colours to all the other conifers. I just wondered whether it's because what you're picking up in those PDF similarities, whether they've got strong seasonal variation due to being deciduous. And because you, so I didn't explain that very well, did I? But Larix is the one conifer in that group which is drops its leaves in winter, so it's a deciduous conifer, whereas all the other ones are evergreen. And all the ones on the right are deciduous; they will drop their leaves in winter. And then Larix looks much more similar in those color codings to the other deciduous ones. So you could just move them about, I think, and I think it supports what you're doing rather than contradicts.
Yeah, I mean, it's good to, I mean, in fact, you are seeing that it's deciduous.
Yeah, exactly.
Yeah. Very
Maybe you already knew that.
No, I didn't know that.
It's very interesting. I mean, one of the challenges when I did this project in science, even though it's English meanings for it, is this when Lam mentioned like the biophysical knowledge of that. So I feel a bit difficult when trying to interpret the results I get. I only see, okay, the jam distance I calculated looks better. And I mean, the variables are more disentangled than the variables of the baseline, but what does that mean? It's difficult for me.
I think the fact that that's deciduous actually supports or everything you've said rather than it's more aligned with all the other deciduous ones. Your distances between the PDFs is down to the deciduousness versus the evergreen nature of the species.
Yeah, I guess I had kind of a follow-up question about the field data. I was just really trying to imagine what was the data that was in, like what kind of scale was the plot, and do you have species information per pixel, or is it whole plots? Like, yeah.
So my understanding is that the data we are using, it has such format. Each row is the like individual spectra of 14 timestamps for an individual set, or maybe an individual pixel, because it extracts the spectra from because for each input data only have like 11 bands, like 1 by 11 spectral bands, and it comes with the species and temporal information, and we have a sample ID for each individual site. So yeah, I think it might come with each single pixels.
And it's like presence, absence of species, or is the percentage like cover like 50% of PCRs, 50% of something else?
No, it's just one entity. For each input data, for each input spectra, it has one species information, like which species it is and corresponding forest type.
Yeah, it's because it's very homogeneous forests.
Yeah, I think I need to look into how the data get derived. But very good question.
Maybe a plantation perhaps.
Yeah, if it's only one species, maybe it's a plantation.
But like usually for doing like field remote sensing, you go like up in the platform and then you point to a tree that you want to know the spectra, and you do like several measurements, and then you average these measurements, and then you have only one tree. I don't know if that's the case, but
Even if it's on Sentinel-2.
yeah, but like what I understand, like those field spectra is like collected in the field, isn't it?
Yes,
That's so is there field spectra and Sentinel-2 spectra, two kind of spectra data, or?
I think only Sentinel-2 spectra.
Okay.
What does field spectrum?
I don't know, because I was,
You have a field spectrometer and you literally go up in a tower above a tree and point it down at the tree.
I think it's Sentinel-2 spectrum.
I guess my question was kind of like related to the fact that, from my understanding, radio transfer RTMs link the like biophysical properties of the forest to a spectra. So like, I guess in order to train this model, you have the Sentinel-2, but also you need from the other end, like some kind of estimation or at least some prior knowledge of the biophysical variables. I guess from whatever that there's something that you did use is the known range of the parameters.
Yeah.
Well, I don't think inform is trained, is it? Inform is sort of
No,
constructed
it's
from
not.
scientific knowledge.
It's informed is a model.
Yeah. I mean, I can see that it's kind of like bottom up, like physics based. I was just wondering, like, I guess when you validate, you don't validate it against actual measurements, but you validate against like prior knowledge of like what is the known literature range of this variable and how they vary through time. And,
Yeah.
Okay,
So there's no supervision or evaluation directly of the biophysical variables, like we can go into the field and say, okay, like here are the actual biophysical variables, and here's the divergence between what the model produced and what we actually measured, but it's more like these distribution, like you've been saying, it's these distributional characteristics.
Yeah, that would be the ideal case, like we can have some biophysical variables to from the field to directly compare.
Yeah.
But unfortunately, so far I didn't have that data.
Yeah, okay.
Mm.
If I could ask just another question too, is on the ablation experiments, it seems like the encoder decoder architecture without the RTM and without and maybe I'm reading this wrong, without RTM, without correction, has a lower mean squared error than anything else, which seems a little bit in conflict with the other things that you've been saying, which is that it helps to have the RTM and the correction, but maybe I'm misunderstanding.
So what's your second half of it?
Oh, it just seems like the without RTM, without correction has the lowest test error
Yeah.
of any of them, and so then I'm confused why you wouldn't just do a learned end-to-end, like full autoencoder structure.
Mm.
Um,
Yeah, that's the
yeah.
first thing we did, because you can have like a vanilla autoencoder
Mm,
to reconstruct the spectra.
Mm.
Actually, for this comparison, we have the same latent dimensions because we aim to learn 7 latent variables.
Mhm.
So for the vanilla autoencoder, also keeps the latent dimension at 7.
Mm.
But if you look into what learned by latent
Oh,
code,
I
it
see.
doesn't carry out any.
So it has really great reconstruction performance,
Yeah.
but there's no separability in terms of the latent variables. You can't map those onto like, this one is crown diameter, this one is whatever.
Or you can then do that by either have many, like a plenty set of ground truths, so that you can train another regression model between the latent codes and the variables.
Yeah,
Or you must still need to dance with the RTM.
I see. So you, because there's no data to train on specifically for the latent variables, no field data, the RTM provides kind of like indirect supervision in that sense, that does provide the disentanglement property that you want. And what you're showing here is that you have almost exactly the same mean squared error. It doesn't change very much to add in RTM and correction. So you're getting the same reconstruction error, but you are also getting disentanglement.
Yeah, I think that what's important is not only the reconstruction accuracy, but also what you can learn from the latent space, yeah, the latent variables. And the RTM here is more like a teacher model that teach how the encoder should learn what the encoder should learn.
Okay, I see. Thank you.
I guess you did it to have a good idea of what is a good mean square error.
Right.
But you wanted to know, are you getting close to the sort of best you could possibly get?
Yeah,
And the plain decoder, the plain autoencoder gives you the very best reconstruction error you could expect with that number of latent variables.
yeah. I mean, I can add some more information because during my write-up, I think in the past few weeks, I tried to submit this to a workshop paper. Also tested that here we only use the RTM as a constraint and the reconstruction and constraint. Also try to embed the temporal information, like to have some conditioned learning of the variables. I mean, that indeed helps to make the MIC loss even smaller, more comparable to the classical autoencoder. But the learning in the latent space doesn't have significant improvement. I guess it's due to like the ill-posed nature of this problem, unless you specify some requirement, some constraints in the latent space saying that, okay, the temporal consistency should look like, like a double logistic function or something like that. You can't just say that, okay, I give you this information by conditioning on this temporal or species information, the model is able to find the right side of the variables by just minimizing the reconstruction loss.
Right. There's not like enough information to properly separate within the latent space.
Yeah.
Interesting.
I also have another question about the RTM itself. So is it so how is this spatial variability encoded in this model, like the vertical structure? Does it suppose the forest has the canopy and other story, or is it more voxel based?
I don't think it's voxel based. It's actually based on a model called prospect and it contains different levels, as I mentioned in my previous slide. Yeah. So yeah, the first model, that's how the leaf model will first model that's output from the leaf model given these input variables, and then further build the canopy models on top of the leaf models, and then it incorporates some forest features to get output. So it's kind of like a combination of previous RTMs.
Had a couple of, sorry, did you have a couple of questions? One is that, we will go with these 7 variables like Clementus, do this. And I notice here that, for example, of the canopy model, only one of 6 different parameters is being considered. And I was just wondering, now that you've done this, how much work, how difficult will it be to say, to explore if you were to add one more parameter to the canopy model? Does this make it, is it going to cause some kind of confounding, so you're unable to invert properly, right? Because the results become worse by adding an extra variable dramatically, right? Or not, maybe they, so instead of having a blind selection, so to speak, of these 7, could be explored to see which others might be brought into that set of 7 without making this results worse.
Yes, good question. At the beginning, I remember we began with, I think, 11 variables to learn. But I have issues now, it looks 11 variables. Then we have the issue that we look into the plot of the learned variables. We find that some of those, so I think the easiest part to learn the variable from the leaf models. It seems that by the nature of the definitions, they are more disentangled with each other, like the representations. But for the forest parameters and some parameters in the canopy, it tends to more difficult to learn them when they are put together to make all these variables learnable. So we began with 11 variables, and then we test the value range. Because at the beginning, I use a default sample range of info model, which is larger than this one. This one has been narrowed down after some experiments. So we also then reduce the variables to learn from 11 to 7 after some experiments. But I think it will be interesting to see like a different combination of variables.
Yeah, I mean, instead of doing ablation, this is an inverse ablation, right? Add one more and see what happens, and maybe say, okay, that's not good. Let's take that away. You have about 10 more. You could try one by one and see which one works, and you can go to 7 to 8, and then it's like optimizing each step of the time. At some point, you say, okay, this is all I can do. But you have a core of 7 that can make it one more. Basically, that makes it more useful, obviously, to be able. And the second thing was, I think we discussed this broadly, but if you could go to the picture showing the previous slide, actually, maybe. Yeah, this one here. Right. No, I'm sorry. This one which shows the RTM as the decoder. You have this slide showing the RTM and decoder. Oh, yeah, maybe this. Okay, maybe it is this kind of raw. Yeah, that's one over there. I mean, F is generic, right? I mean, from your perspective, F could be anything. Right, any deterministic, actually in your case, it's not even, it's a deterministic forward model, right? It's not deterministic in the reverse direction, but any deterministic forward model could be inverted as long as you can regularize the inputs because of the fact that, it's not one-to-one, essentially, right? So given all this work you've done, right, how generalizable is this to other forward models for other things? For example, ray tracing is a forward model, right? Ray tracing.
More information about ray tracing.
Ray tracing is you have a scene, you have a light source, and you're going to basically recreate the scene. You're going to find out where the rays come to. So from your point of view, you're going to basically figure out what are you going to see if you're standing over there, because you're going to have all these rays of light coming out. And that's basically how computer vision images are created, right? That's a forward model which is very well defined because your reflections, your specular reflection, the diffusions, all these people, and you say, okay, that's what I'm going to see. That's how we get these photorealistic images. It will be very interesting to invert it, right? In other words, if you're given what you see, can you go back and create the physical space? Right? That's the inverse model. It's ill-posed, of course.
Well, I'm very annoyed that you got to say that first.
I asked you for help first, and you said you had any questions.
No, you give me a chance. Well, I can have one. I've written that down already. It's in an email to.
I grant you priority.
We'll share. So the extra idea perhaps is that there's such a thing as a differentiable renderer.
Okay.
So normally in computer graphics, you don't bother with the differential, all kinds of things are not differentiable.
That's
like, if something goes into shadow, that's a kind of sudden change.
Right.
Won't be differentiable, but people like, I think Michael Black in Germany was the first to work out a differentiable renderer, and if you have that, then you can use all the tricks that you can put it in PyTorch. You can use all the tricks that you used before to invert. So yes, I think that's a nice thought.
I mean, that basically allows you to do one shot in 3D modeling, which is pretty crazy. But I mean, also the other physical models out there, ray tracing is just an example, but there are many other for processes, for physical processes.
But that's a bridge to this year's work. We're planning to render.
Yes, that's true. Yeah, but I mean, it's a different approach completely then, right? It's using a differentiable renderer rather than a direct AI. And if you want to do basically go from monocular vision to 3D reconstruction, you can use this as the possible pathway for that too.
Oh, really?
Yes. I think Adam just gave you the secret to that, to use a differential renderer.
Yeah. I still remember like during Amran's project, Kasha mentioned that some people from DAMT told him that this problem is quite hard. So I'm not sure like what kind of models the people from DAMT are referring to. If they are implementing in PyTorch, maybe we can plug it in to see how it goes.
Yeah, I mean, for example, just to give you a sense of this, what Emilio is talking about, the mixing models, which are these are models for mid-latitude circulation. And I did this ocean mixing current, right?
We're doing the original overturning circulation.
Okay, meridional circulation, but think of it as a forward model. I'm going to give you the input, and you plug it to the model, gives you some output. Now I want to take with that output what's are the parameters, the geophysical variables corresponding,
Right.
which is the radiative forcings, the density of water. I don't know, there's some parameters which are
Like as a standard for the numerical simulation.
Yeah. So this says that F is a numerical simulation, essentially. Any numerical simulation, I can invert it as long as it is expressed in a differentiable form. So the thing that you had to do was to take the numpy and make it PyTorch with a differential. Right. So if you take any forward path, which is at least expressible in PyTorch and therefore differentiable, we get into the possibility of inverting it. So this is a very, very powerful tool. Just saying.
Yeah, I mean, something I didn't mention in this slide. So working with info in practice, you will always have some practical issues. First is forward paths, right? Because we struggle a bit to narrow down the range in order to make sure that the learned variables make sense. But this range in forward paths has been modified several times after some experiments. Also, thanks to Clement's profound knowledge in this domain, so the known ranges. So actually, what we are learning is a scaling factor, from 0 to 1. So then we're rescaling that back to the known range of the variables. So this helps us to reduce, mitigate the ill-posed nature of the inversion problems. Also, even the info model itself is differentiable, but in the back propagation, you still encounter some issues I didn't mention in the slide. Because let's say for this model, it contains many exponential logarithm, these kind of operations, which means that when some of your variables, the values was at some extreme ranges, you get the back propagation. In mathematical theory, you can still get gradients, but in PyTorch, it gives you some not a number or infinity or something like that. So we also work around like that.
So the gradients are like exploding or.
Gradient explosion, anyways, something like that. So also work around with that to stabilize this back propagation process. So if you have logarithm or exponentials, it can still, if the gradient is, let's say, infinite or something, we replace that with some smaller gradients near to zero value, and then help it to jump over that unstable point and then keep optimizing. Yeah.
I mean, actually, Inform is a kind of a renderer, isn't it? And I imagine it must have shadowing effects included in it, because you've got, I think you had the angle of the sun or something like that, didn't you?
Yeah.
So there should be shadow. So I'm surprised it is differentiable. I would have thought there would be some areas of its parameter space where it's not smooth.
Well, it's not actually. So this thing I mentioned here, this exponential integral function itself is not differentiable.
No.
So I convert that to PyTorch in order to calculate that gradient. I look online with how to use an approximation function to calculate its gradient. So kind of like I define the function to calculate the derivative myself. So use some approximation functions to use.
Yeah, I think you're right. I mean, I do remember you're running into these numerical issues and having to, jump past them. So in fact, it is not, so naive Inform is not differentiable, but you have to do some careful tuning, smoothing out. But it's still,
Yeah.
Can I make a question moving back from the environmental side and a little bit away from the machine learning? I'm sorry for that. So it's really cool, your work, like I really enjoyed it a lot. But like, I think part of the audience, including myself, is very interested in tropical forests, which like are more complicated. And then in terms of Eping says, like you have a pixel that is like, it's not a pure forest, you have a much more complicated vertical structure. And then like you start having two problems with those Inform and any RTM models that you have. Like first, you have the sensor limitations, because now you have the signal that is saturated and you don't have like the linear response as you do with forests more temperate. And then you have the problems with the bias of the model itself. So do you think that your approach will be able to kind of like have a better estimates? For example, if you had like, I think Dr. Muto was producing a software where you put like a forest plot and you give you the Sentinel spectra for it. And then you have like, for example, David, I think is part of forest, tropical forest plots, isn't it? Like there's the worldwide where you have like tropical plots everywhere. So if we extract the Sentinel spectra from those places, you have all of the parameters. So you think your model would be able to solve those problems in some way and correct those biases we haven't been able to do it?
Yeah, I mean, it's interesting to experiment and try if we have some data, especially with some ground truth measurements.
So I mean, Felipe does have 700 plots which have been measured, right?
Yeah.
I mean, and these are some of these are LiDAR, but they're all I mean, in principle, Sentinel did go over them. So in principle, it is possible to get the spectral data and the ground truth for those plots at least.
Yeah, there's also this like worldwide effort where they distributed plots like of forests like across the tropics. So you could also like use View tool for extracting the Sentinel data, and you just use the data people have been collecting and see if it works. I mean, it would be great.
Yeah.
Because like temperate forests, like it's very amazing, but like it's like a more solved problem. But for tropical forests, a very ongoing big problem on how to retrieve those information based on satellite information because of the saturation of the signal, and then the problem with your methodology. So when it's sum up, we got like really bad estimates.
Yeah.
I think the two of you should talk and see whether you can use the new data you have with We've been grilling Mihan for half an hour. So thank you very much.